Hello, in this video we're going to take a look at a few integrals, 2 to be specific, involving the natural log. So our first one here, we have the integral of e to the x divided by 3 times e to the x plus 2. So at the first glance it looks a little complicated. It's got a couple exponential functions, it's a quotient, but really it's not that bad. And here's the tip I can give you. Anytime you see a quotient function, that is a function where you have a function divided by a function in the denominator, there's a good chance it's going to be a natural log integral, which means if you can force it to be of the form 1 over u, it's going to equal the natural log of u, and it won't be that bad. So the goal is then to force it of the form 1 over u, which means let the denominator equal u. Now before we proceed, I do want to caution that just because it's a quotient doesn't mean it's going to be natural log. The other common one it could be is an inverse trigonometric function, like sine inverse, cosine inverse, tangent inverse. And that's a big possibility. If it's going to be that, though, those inverse trig integrals have a very distinct form. And as you work with them more, you learn to recognize that form, and you'll kind of see right away or pretty quickly if the integral is an inverse trig. Otherwise, it'll be an inverse trig, a natural log, and of course there's other things. It could be a simple power rule like 1 over x squared, for instance. But those are the big hitters for these. So it's always good to just try out if it's going to be natural log. And how do you try that out? Well, you let u equal your denominator and just see where it goes. If you mess up, that's okay. Just try again. But it's a good place to start. So I let u equal 3 times e to the x plus 2. Take the derivative, and I get 3 times e to the x. Derivative of 2 is 0. So we are right here. Well, that's not exactly what I have, but I can deal with that constant of 3. I just divide both sides by 3, and I end up with du divided by 3 is equal to e to the x times dx. And what do you know? E to the x dx does appear in my original integral. Well, that means I can make the substitution. And that divided by 3, I'm just going to say that's 1/3 out front. I can factor out a constant. You can always do that with integrals. It's no problem. No big deal. So then I have du divided by u. And you look at that and you're like, piece of cake. I know what that is. Anytime I see 1 over u, I can just say that's equal to the natural log of u plus c. Remembering absolute value bars. Absolute value bars are there because a natural log cannot be negative. So we got to ensure that whatever I put in for u, and eventually whatever I put in for x, makes the inside of the natural log positive. So now I'm going to plug in my u, 3 times e to the x plus 2. Remember my plus c, and voila. Now one last thing I will say is I can actually rewrite this as 1/3 times the natural log of parentheses 3 times e to the x plus 2. So I took away the absolute value bars. And in this specific case, that's okay. Because in fact, that little chunk, 3 times e to the x plus 2, no matter what I put in for x, that's going to be positive. Always. Think about it. All right? Think about the graph of e to the x. That's the easiest way to think about this. Well, here's what the graph kind of looks like. Rough sketch. But that's never negative. See, all the y values, no matter what I put in for x, the y value is always positive, always above the x-axis. And so if I take that, e to the x, and I multiply by 3, it's still going to be positive. If I add 2, it's still going to be positive. So I do that little mind calculation to figure out, well, that 3 times e to the x plus 2 is always positive. Therefore, you can write it without the absolute value bars. And in math, it's sort of just a good thing if you can write it, your final answer, with the least amount of stipulations, kind of the least amount of requirements of your function. So that absolute value added a requirement. It added that this extra superfluous must be positive information. It's superfluous in this one because the inside of a natural log is always positive anyways. All right, so that absolute value to parentheses part is unnecessary, but a good little touch. All right, the second one. This one's a definite integral. And we have the integral of 1 divided by x times the square root of the natural log of x. And this is definite because it's going from e to the 4th. All right, so based on the advice I gave you in the last one, this is a quotient, so you think, well, maybe natural log. So you would say, let's let u equal x times the square root of natural log of x. And then I take derivative. Well, derivative of that is pretty complicated. It's a product rule. And that clearly does not appear in my integral. So, as I said before, no big deal. Just back up and let's try again. So it's not a natural log here. What could it be? Well, this takes some i's, but if you let u equal natural log of x, what do you know to be the derivative of natural log? Well, 1 over x. And it's a little bit hard to see, but I did write in this 1, and you can see I have a 1 over x right there. So this substitution is going to work. I'm going to be able to say that this integral now is equal to du divided by the square root of u. Okay, and actually, when I put these bounds, e to the fourth and e, that's not technically correct right now. That is the bounds as if x was my variable, but as soon as I chose this u, it changed. Well, what did it change to? We can figure that out. We can look at this u substitution and we can say, well, when x is e to the fourth, what is u? You know that natural log and exponentials cancel out, so this is equal to 4. So my upper bound is actually 4. And down low, I can use natural log of e. This is for the right endpoint. Well, this is just equal to 1. So in fact, I need to change these bounds, now that I made the u substitution, to be going from 1 to 4 of 1 over the square root of u times du. All right, so there I changed my integrations, which means I can leave this in terms of u when I evaluate it. If you wanted to substitute back in for u, you could just leave the bounds the same for x. All right, so let's integrate this. I'm going to write it one more time to help us out, because this is equal to u to the negative 1/2 du. I write it like that because, well, that's just a power rule, and that's pretty easy to do. Piece of cake, you might say. I will erase my integral symbol since we're going to take the integral. All right, power rule. So you add 1 to the exponent and then divide by that number. And we're going to evaluate it from 1 to 4. Well, before I evaluate it, dividing by 1/2 is the same as multiplying by 1/2. So it becomes 2 times u to the 1/2 from 1 to 4. And this is where I was saying before, I could leave it as e to the fourth, like here, to e, if I would plug in what u equals and keep it in terms of x. Because x goes from e to e to the fourth, but u goes from 1 to 4. All right, so we're going to keep it this way because it works out really, really nicely, actually. Because you have now fundamental theorem, you're going to go from evaluating at 4 minus evaluating at 1. So that's our fundamental theorem of calculus, f of b minus f of a. Well, the 1/2 power, that's just the square root, so it's 2 times 2 minus 2 times 1 gives me 4 minus 2 is equal to 2. Who would have thought that complicated looking integral from the start would just equal 2 in the end? Alright, I hope this video gave you a couple looks at some different natural log integrals, whether it's going to be a natural log at the final end or you let u equal natural log. Hope this gave you some looks at that and helped a little bit.